Hey everybody, this is Larry. This is me going with Q4 of the weekly contest 334. Minimum time to visit a cell in a grid. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem. Yeah, so this one is very cleverly disguised. It's a very tricky problem for sure. It took me a long time. You can watch me solve it live next to kind of see where the time went. But I think the first thing to notice, of course, is that it's a graph problem going from top left to bottom right. I actually misread this initially. I thought it was a connect. I thought this was like a different problem. Just put it that way, where it's like the one where you binary search on the connected components, or you could use union find, where basically what is the earliest time you get to the thing where the cell opens at that time, you can say, right? And also part of that is that you're not forced to move left, right, or make a move, where in this case you are. So it turns out that, it took me a little bit of time, but it turns out that there's only one case in which there's -1, or that means that you cannot reach, because and it's basically, if you're in the first cell, you cannot go to the left, you cannot go to the right, you cannot go bottom, then you're stuck there forever and you return -1. That is the only case. Why? Because if you can go to one of those cells, then you can always go left, right, left, right, left, right, left, right, left, right, right? So you can go forever left, right, until you can go somewhere else, right? That's basically the philosophy behind it. Okay, so but that's not enough, right? That is enough, but there's a second portion of this problem, which is that, well, if you do a naive Dijkstra or breadth first search or something, you might go back and forth a long time, and you really don't want to visit everything. You really don't want to visit. You really don't want to spend the time to go back and forth, really, right? In code, in implementation. So that's basically the hard part of it, as you might, that you might have thought about that, and you'll be like, well, this time limit's exceeded otherwise, right? So the first observation that I thought, and actually, let me pull up a drawing thing. Maybe it'll make it a little bit easier. The way that I thought about it is actually, I never know how to make these things bigger. Oops. Okay, maybe this is fine. Okay, so the first thing that I thought is that, and it took me a little bit of time to get to this point, to be honest. But basically, the idea is that, okay, let's say that we're able to kind of hop back and forth. Zoom in, this is so big. Let's say we are able to hop back and forth between these two, right, forever. What does that mean? For me, one thing that I thought about, and let's just say this is 10 for now, and this is 51, this is 32, something big, right? What does that mean? That means that what is the first time that we can get to here, right? Well, the one observation that I made was that actually this is a checkerboard, right? What do I mean? That means that let's just say I paint in some colors. Let's say this one, right? So now we have a checkerboard. I use red because I will use black, sorry friends. Also, it might mess up with the numbers anyway. So I don't know, whatever, right? But basically the idea is that you start at 0 here, right? Let me change the color again. You start at this number 0 here at time 0. That means that this is odd, right? But this also means that this is even. So that means that every right square is going to be, if you could reach it, is going to be even, right? And every red square, in this case, is going to be odd. So knowing that, that's basic, and I actually spent some time trying to figure this out. with respect to the implementation, which we'll go over in a second. But basically now it means that if we're able to go back and forth, meaning that the first initial square is good, then here, going to here, it just means that we want the next even number that is bigger than or equal to 32, right? I kind of did, yeah. But I kind of did this a little bit weird. Or I didn't take a, let me do another one. So let's add a 20 and 30, right? Just to kind of make it more clear. So then here, so that means that we get to this square at time 32 because, or at least we push it as a Dijkstra, right? And here, we get here at time 10, right? Because that is the next even number, because you can imagine that we're going back and forth. Here, this the one cell, let me change the color again. The one cell, you know, could be 1, 3, 5, 7, and then 9, and then finally jump here to the 10, right? That is what I mean by all the red squares are odd numbers. And by that logic, going from the 10 to the 20, now you want the I think I circled the wrong one, but you get the idea. Because here, now from a even square to an odd square, now this has to be 21. So we get to here in 21 time. So then that's basically it. We fill it out. This gets to here in 22, 23, and then you're done. Yeah. So that's basically the logic behind it. And the visualization. I didn't put on the visualization. I am being dumb today. Okay, this is what I drew. How did I salvage this? Okay, well, I don't know what to say. Here, I'm just gonna let you look at this for about 20 seconds while I hang my head in shame, and then you can maybe digest what I said because I forgot to pull up the painting. But yeah, but basically the white squares are even cells, the red squares are odd cells, and you can kind of see what I mean by that. You know, when you jump back and forth on the one square, it's going to be 1, 3, 5, 7, 9, 11, ... So then when you go to the 32 square, it has to be an even number. You know, you go forever, you're going to go to 31, and then you go there for 32. And then also the same for 10. It goes to 9, and it goes to 10. And then 10, it goes to, you know, 10 goes to 10, 12, 14, ... all the way to 20. So then 20 goes to the 20 space with 21. And then just 22, 23. Hopefully now that you see the visualization, it helps. But yeah, let me know what you think. Let me know if you have any questions. I'm tired. Sorry, friends. I am going to now actually take it off and look at the code. But yeah, but otherwise it just becomes straightforward Dijkstra's algorithm because you're just trying to, because now in a way, instead of having a unweighted edges, you have these edges of a variable, well, it just has a rate, right? Where the rate is the distance that you can calculate between them. And then that leads itself to the shortest path in a weighted graph. And then now this is Dijkstra, right? Yeah. And as Dijkstra, I initially set the upper left to 0, 0, 0. I push it in the heap. I want to check to make sure that it is good first. And basically, this is really fancy, but it just looks up, down, left, right from the initial square to see if you can get there, which is meaning that the grid is 1 or 0. If you cannot, then you return -1. Otherwise, you just run straightforward Dijkstra. Yeah. This is the heap. This is the return condition, and you should always reach it anyway. I don't think this is possible, but just in case, I guess. This makes sure that we only process each node once. This is the direction piece. Hopefully I don't have any. If I find a typo now, I'll be very sad. But in any case, yeah. up, down, left, right, if this is within bounds. If d+1 is already bigger than a thing, then we just update it to d+1. Otherwise, we set the grid to that number which is bigger than d+1, and then we just make sure that the parity is different. Then we add 1. I wrote this in a really funky way the first time. You could see in the video. Cost me a 5-minute penalty. And then I kind of just clean it up with a better visualization mentally. And, am I showing the screen? Okay, I'm just so paranoid now. Two production mistake today. But in any case, yeah, and this is just Dijkstra as well. This is, if we want to update it, then we just update it. Yeah, and yeah, this is going to be yi log yi. This is regular Dijkstra, where yi is 4 times v, so v log yi-ish, or v log v-ish in that case. Time and linear space, which is r times c, which is also the number. R times c is v because, well, that's the number of cells, so you can say it in 2 ways, which I'll write down. Let me also make it smaller so you can see more of it. Maybe this is good enough. But yeah, this is all of v log v time, also all of rc log rc time, and space, it is just all of v, which is all of rc. Right? Yeah. Maybe a little bit more because of the way we do Dijkstra, but no, it should be still R times C. At most, it just updates each cell 4 times. But yeah, that's all I have for this one. Let me know what you think, and you can watch me solve it live in the contest now. Okay. This is annoying. This is gonna piss people off. I'm copying my code for union find is what I'm doing, in case you're wondering. Wait, what? Did I misunderstand this? Why is this impossible? Maybe I misunderstood this. Let's see. Only when the time you visit is greater. Oh, I misunderstood this actually, maybe. I misunderstood this. Okay. Oh wait, no. Yeah, no, I misunderstood this. Because you cannot move at 0. Let's think about this. Yeah, let's keep it here for now. People haven't counted yet. You must move. Okay. And you could go back and forth. So really, the impossible ones are not that common. 10 to the 5th, it can go really long. Well, 10 to the 5th. So maybe like 2 times that. Really. Is it dexterous? I don't think so. This is an annoying one. Definitely misread it, but okay. I mean, it could be dexterous, but with some funky things. That's really weird. There's no 3 cycles. There's 2 cycles. Okay, so there's only odd and even. Okay. Maybe it's dexterous. With 2 states. First state and then now. Yeah, okay. I think I got it, maybe. Someone got it. Okay, well, people are very smart. So you started. And then space. What am I doing? Really, there's only one impossible case, I think. These two cells. Okay. You can go back and forth otherwise. Okay, how do I just check that out? So otherwise, you can always just go back and forth, I think. Okay. The parity is actually a fake thing. There's no parity. Parity is determined by the space. You can't go there any other way. So that means that. So if which is good, then we just do. Otherwise, if it's smaller, then we're going to even to odd. Something like this, maybe. I think it's actually this, but it could be wrong. We'll test it. So we go. I think this is. Something like this. We'll have to make. Just want to make sure that. I think we're mostly done, but just want to make sure that doesn't inspire confidence. Oh, of course, this is at the beginning. Okay, so I think the critical one is 1, 3, 6. I mean, that part is right, but 1, 3 is 6. So 1, 3 to 5 cannot go to 4. So that's just wrong. So I definitely got this wrong. Because basically this has to be I mean, that would have been the wrong answer anyway, so that's fine, but... my math sucks. Okay. One, 3 should be 6, and then this should be 7. And this is mostly right, but I'm off by 1. Somewhere. Because even this is wrong, right? So let's actually do another case that's more obvious. That's kind of a weird thing to need to do, but okay, fine. That's really not right. 1, 2, 2. I mean, this is 5. This. 0, 1, 2, 3, 4, 5, 6. Okay. Maybe I'm happy now with my print. Still could be wrong, to be honest, but I'm happier. Okay. Huh. What am I off by? I mean, it's this is so sketch. That's probably why I'm wrong, but the idea is right, but my math is that bad. So basically, we want to, let's rephrase this. We want to I should have written it that way, actually. That was kind of silly of me. I was trying to do too smart. Yeah, I mean, I had the idea. I just was silly about it. Had an opportunity there, but the wrong answer is going to cost a lot. Yeah, good job, Vasco. Chi Impact was doing pretty well. I knew how to do it too. That's the sad part. Like I knew I didn't know how to do that part, but I probably should have just really slowed it down. I was rushing it too much near the end. Yeah. I mean, it's 38, and then it's gonna the 5-minute penalty. If it wasn't for the 5-minute penalty, I probably would have been okay. But the 5-minute penalty means that I'm gonna drop quite a bit. I don't think it's that bad. It's yeah, people did it very quickly even. Jeez. I probably could have done it better, but implementation's been pretty bad lately. But I mean that was okay. I think yeah, I don't know. I mean, I think I have to look at the tapes to see where I spend my time, to be honest. But because sometimes I think I spend time here and there, but really, like, there are a lot of other things. Right now, at the highest, I could be as 30th or 31st rather, and it's just gonna keep going lower. Yeah. I want to see where I spend my time because I think implementation wise, after I kind of was convinced, it was pretty okay. I don't think it was that bad. And I guess that I didn't realize that it has to be at least 2 because then this function's easier. This is just grid 1, 0, and 0, 1, and then everything else is straightforward. I did some funky math instead of this, and that cost me 5 minutes and another minute to debug. But I knew where it was because that was the only sketchy part, unless I made some other silly mistakes, which happened. So that's why I was pretty confident about it. Anyway, thanks for watching. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem, this explanation, and this contest. Yeah, stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye-bye.